Hello students, in continuation with my lecture on the topic propagation of electromagnetic wave in a conducting media, we have studied that in a conducting media, the electromagnetic wave decays exponentially first. The charges are supposed to be zero when we are discussing conducting media, and the propagation constant vector is complex in nature, consisting of real part and imaginary part. Now, let us continue further and see what is important from the exam point of view. Exam point of view, three things are important. Propagation constant vector is complex in nature, Maxwell's equations in conducting media, and the electric and magnetic field equations for the EMT wave in conducting media. Now, what we will do is we will see the case for a good conducting media. Sigma, that is conductivity, is very greater than omega epsilon. That means other way around, you can say omega epsilon upon sigma is very much less than 1. Hence, in propagation constant K, we can neglect this term because this will be very small in value, hence it can be neglected. So, for K equal to alpha plus I beta, if we square on both the sides, we get K square is equal to alpha square minus beta square plus 2 alpha I beta. Now, we take the real and imaginary parts of the above expression and we compare the same, because K is complex in nature. So when we compare the real and imaginary parts here, we get K equal to under root I mu epsilon sigma omega. Since the electric and magnetic fields are perpendicular to each other, theta becomes equal to 90 degree. Using the formula, E equal to I, e to the power of I theta is equal to cos theta plus I sin theta when theta is 90 degree. Cos 90 plus I sin 90 becomes equal to I, because cos 90 is 0 and sin 90 is 1. So I is equal to cos 90 degree plus I sin 90 degree, and taking under root on both the sides and using De Morgan's theorem, we get I to the power of half is equal to cos 45 degree plus I sin 45 degree. And then K is under root I mu sigma omega. Here we put the value of under root I, what we have got up here, and putting numerical value of cos 45 degree and sin 45 degree, we get the answer for K as under root omega mu sigma into 1 upon under root 2 plus I upon under root 2. Once again, we compare the real and imaginary parts and we find that alpha is equal to beta is equal to under root omega mu sigma upon 2. Next, we find the value for alpha and beta. We can put in this expression and write the expression as e to the power of minus under root omega mu sigma upon 2z and phase factor e to the power of minus j under root omega mu sigma upon 2z, which is indicating that the wave is attenuated exponentially and retarded linearly in phase with increasing Z due to large conductivity for good conductors. The velocity of propagation for good conductor is given by V is equal to omega upon beta, that is frequency upon phase factor, which is equal to under root 2 omega upon mu sigma. Refractive index of conducting media is equal to C upon V, which is equal to C into under root mu sigma upon 2 omega. Omega can also be written in terms of linear frequency as omega equal to 2 pi f. Now, show that electromagnetic wave damps exponentially in a conducting media. The distance it takes to reduce the amplitude by a factor of 1 upon E is known as its skin depth, and the term 1 upon beta measures the depth at which electromagnetic waves entering a conductor is damped to 1 upon E equal to 0.369. So basically it is that for good conductors, the skin depth measures how far the wave is penetrating into the conductor, and it is given by under root 2 upon omega mu sigma, or in terms of linear frequency, skin depth is given by del equal to under root 1 upon pi f mu sigma. From this expression, it is clear that the skin depth for good conductor depends upon conductivity and frequency. Here you can see that how it is decaying exponentially for a good conductor. Now we conclude that the electromagnetic wave damps exponentially in a conducting media. This numerical has been asked many times in your exam. It is a simple numerical with a very simple application of the formulas. You only have to be careful while keeping the values given in the equation. A uniform plane electromagnetic wave is propagating in a medium whose conductivity is 2 into 10 to the power of minus 3 Siemens per meter. Epsilon is 80 times of epsilon naught, and mu is equal to mu s, and f is equal to 10 kilohertz. Now you have to calculate attenuation constant, phase constant, propagation constant, intrinsic impedance, wavelength, and velocity. So everything is there in this numerical. Let us begin. Sigma is 2 into 10 to the power of minus 3. Epsilon is 80 times epsilon naught. Frequency is 10 kilohertz, which we will change into hertz. So we will multiply it by 10 to the power of 3. Epsilon naught is equal to 8.85 into 10 to the power of minus 12. Mu naught is equal to 4 pi into 10 to the power of minus 7. We will put all these numerical values in the formulas, and accordingly we will get the answers, as you can see here on the screen. What all is there for intrinsic impedance, wavelength, and wave velocity. A very similar numerical also has been asked on this topic. Same procedure for attenuation constant equal to under root pi f mu sigma, and then we put the values and we simply get the answer. For PDF of this file or any other problem, please do contact us. Thank you.